on to your central tendency descriptive statistics. This is your basic mean, median, and mode. We're going to break down what the three central tendency statistics communicate and when you might want to use one or the other. So any measure of central tendency can also be termed an average. So an average is one value, one numerical value that's meant to represent a group of scores. So essentially, it's a descriptive summary statistic. It's meant to be a value that describes something about a central location or where most of the values in your data distribution are located. It's usually meant to be somewhere in the numerical center of the distribution of scores, but not always. But it is meant to be a good summary or representation of a set of scores. Now, it's important to note that the term averaged is used interchangeably with mean. Technically, the mean, median, and mode are all types of averages. So typically when people say average, they're talking about the arithmetical mean, but technically both the median and the mode are also kinds of averages. So for the purpose of clarity in this class, I'll make sure to try and only use mean when I'm talking about the mean and not accidentally say average, since technically average can refer to all three central tendency statistics. Okay, so like I said, your central tendency statistics are your mode, median, and mean. This is hopefully nothing earth-shatteringly new or difficult, but we are going to review what the three central tendency statistics are, how you derive them, and why they're useful or why they might sometimes not be so useful. And again, the term average would apply to all three of these central tendency statistics. So again, try and make sure not to use average and mean interchangeably, because technically the mean is an average, but not all averages are means. So let's start with the mode. The mode is going to be the score that occurs most frequently in your distribution. So if, let's say, you have a series of these 10 scores, the idea is I just pick whichever score happened the most. So in this case, the mode is 17 because it happened, let's see, 3 times, and no other scores appeared as frequently. A data set can have multiple modes if there are two unique scores that appear the same amount of times and they sort of both tied for first in terms of how many times that value appeared. If so, that data would be called bimodal if you had two modes. The mode is going to be particularly useful when you're trying to describe or get an average from nominal data. If you have categorical based data, you really can't calculate a mean because this is essentially not quantitative data. So if, for example, you're polling people on their soft drink preferences, what you have are a series of categorical responses. Yes, you could create a frequency distribution, but this is still ultimately qualitative, non-quantitative data. So how would you be able to get a central tendency statistic? Well, you can just figure out which value appeared the most often. So you can create the mode for nominal data. Right, in this case, the mode is not quantitative. It's just whichever category appeared more than any other category. So if you do have data that looks like this, where you just have a series of categorical responses, your options would be to make a frequency distribution, or you could derive the mode as a way to generally describe your data set. So like I said, the mode is particularly useful when you're dealing with a categorical variable that you can't subject to any more quantitative analysis. Additionally, as opposed to the mean and the median, the mode is a score that did in fact appear in your data set. And it is informative. You do know that any score picked at random from your data set is more likely than any of the others to be the mode. So it does give you some information. It's not perfect, though. This is going to be the running theme, that there's sort of upsides and downsides to any approach for central tendency statistic. So one problem with the mode is that it does not work very well when you have many scores in the distribution that have the same frequency. Let's say you have a set of scores like this, where many scores appear an equal amount of time and they're sort of all tied for first. Well, in this case, all of the scores that appear the same amount of times. It appears that every single score appears twice. What that means is that there's either no mode or that all scores are the mode. Theoretically, it doesn't matter which because it's not informative either way you slice it. The mode for data that looks like this is basically entirely useless. Additionally, the mode kind of throws out a lot of the information present in your data set. It only takes into account that single score that appears the most often, and it sort of disregards everything else. So the mode might actually be misrepresentative of your distribution of scores. Let's say you have a data set like this, where for some reason there's an outlier of a score that appears more often than all the rest, right? The mode here is 6, but most of the other scores are nowhere near that. So if you were to just use 6 as a summary statistic for this data, it is pretty misleading and it doesn't accurately capture what's going on with your distribution of scores. The median, on the other hand, is going to be the score that represents the value in the data set that has 50% of scores beneath it, and as such, 50% of scores above it. It essentially splits your distribution in perfect half, with half of the scores above it and half the scores below it. The way that you can derive the mean really easily with quantitative data is you arrange the scores in numerical order. The median is just the one in the middle. So let's say you have this set of 5 scores. You would just arrange it in numerical order, ascending or descending, doesn't matter. And then the score right there, smack dab in the middle, is 560, right? That 560 is smack dab in the middle. There's half of the scores beneath it and half of the scores above it. So 560 is the median. If there's an even number of scores, though, you might be asking yourself, what does it mean to be perfectly in the middle? Well, you have to find the middle of the two middle scores. So you do the same thing. You arrange the scores in numerical order, and then you figure out what is perfectly halfway in the middle. Even if it's not a score in the data set, that is your median. So in this case, the median is the score halfway in between that 540 and 560. So the median is 550. Again, 550 did not actually appear in the data set, but that is the median because that is the score that would, with perfect symmetry, have 50% of the scores beneath it and 50% of the scores above it. Now, I mentioned percentiles briefly when I was talking about graphics. This is relevant when talking about the median because the median is a specific percentile. Like I said, a percentile is any score that has a particular percentage of scores beneath it. So this can be any percentage. Again, maybe when you are trying to take the SAT or the ACT, or when you take the GRE for grad school, you say to yourself, I really want to make it into the 90th percentile because that indicates you're sort of at the top. So a percentile can be any percentage, but thinking about the median is just a specific percentage. It's just the 50th percentile. So percentiles are in general useful when you are motivated to know the percentage of scores that lie above or below any particular score in the data set. Again, standardized tests are a major example where percentiles are used. Essentially, instead of using your raw score for how you performed on the exam, the idea is the percentile sort of compares you to all of the people who took the test concurrently the same year that you did. So it's just a different way to depict what your outcome was on the ACT or the GRE. Okay, again, the median is an example of a percentile. The median is the 50th percentile. So the median is just an example of a specific percentile. It is the 50th. So the median, the 50th percentile, those terms are interchangeable. So percentile-based data is used for various variables. For example, you might be interested in taking income-based data and transforming it into percentiles. Again, this is just a way that you can chunk the participants in your data set into nice, clean percentile groups. So for example, this is a really cool graphic I found that basically depicts career earnings in various ascending educational degrees between women and men. So the basic point that this graphic is trying to communicate, that for both men and women, as you achieve more advanced degrees, you do tend to see higher income. But as you can see, there's a pretty stark difference between the cap for women at any particular degree versus the cap for men. You basically see that when compared to men, you can see that women's earnings don't sort of rise as much as men's do as they rise through these educational ranks. Again, so you might see income-based data as chunking people into 25th percentiles, the median, and the 75th percentile, What this essentially accomplishes is people below the 25th percentile could be the quote unquote low earners, and the 75th percentile, the quote unquote high earners. Again, it's just a way to break down your data in a way that's meant to communicate and describe your data effectively. Again, you do often see percentile-based data with standardized test scores. And then here's a fun one that I found. I found some research on music preferences and their relationship to performance on the SAT. So again, this data depicts median SAT score, and then it compares students who have various musical preferences to that median overall SAT score, and you can basically compare these various musical preference groups based on where they fall above or below that general median. So you can see that people who like alt and indie, their SAT average is oriented a little bit higher than in general versus people who like punk. My hands in the air. I feel very attacked. I like punk rock music, but I think I did okay at the SAT, so I don't relate to this data. But overall, the research indicates that people who report liking punk rock music, their average on the SAT is oriented a little bit lower than the overall average. So again, the median can be really useful for depicting somewhat kind of complicated data. It's just about how it fits in and what you're trying to visualize. So some advantages of the median that would make it useful: it's relatively unaffected by extreme scores or outliers in the data. So for example, if you have these two distributions of scores that are identical except for one rogue outlier at the end, they have the same median. So the median kind of effectively communicates that these data sets are pretty similar. So you might be asking yourself, when would you want to have your data unaffected by the outlier? It really just depends. If that 120 for some reason was a legitimate score in your data set, yeah, the median would sort of disregard. The median is sort of disregarding that valuable information. If that 120, on the other hand, is like someone in your survey who fell asleep and as such took a lot longer to respond to a question, you might want to make sure that your analysis. Jade! I swear, I will put you outside. Okay? You're cool. All right, so, sorry, it's basically just about asking yourself whether or not that extreme score belongs in your data set or not. So this is going to be a particularly useful way of communicating about your data when you have a variable in which your extreme scores are possible, but they either kind of don't mean anything or you think they're skewing the data too much to be entirely accurate. So something like reaction time studies. As I just mentioned, if you have a reaction time study where if participants are responding to the onset of a stimuli and you're basically measuring in milliseconds how long it took them to respond, if you had one participant that was taking like several seconds to respond and was much, much slower than everyone else, well, you might say to yourself that that participant is probably falling asleep and you wouldn't really want to include their data in your analysis. So something like a reaction time study where extreme scores are probably problematic cases that shouldn't be impacting your average, the median is great. Additionally, you tend to see median used very often as an average measure for income. This tends to be the ideal way to talk about income because if you're talking about income in, let's say, the United States, if you were to take the mean, average income is going to be heavily skewed by about to be trillionaire Jeff Bezos, Bill Gates, Mark Zuckerberg, etc. And those extremely high earnings would artificially inflate our central tendency statistic for what is actually the average income. The fact that Jeff Bezos is a trillionaire would artificially inflate our sense of where most people's income is. So you tend to see the median used to depict income instead because it's not quite as affected by the presence of those extreme megatrillionaires. Now, problems with the median, one is that it's based on more so how many scores there are in the data set, right? Again, the median is what splits the scores such that 50% of the scores are above and 50% is below. So it essentially is going to be partially derived based on how many scores you have in your data set. And you sort of discount the values of the scores themselves. So in that sense, just like the mode, you're throwing out a lot of information. You lose all of the information about the actual values of all of the other scores in your data set. So for example, again, you might have two data sets that when you're comparing them, they have the same median, but they're actually very, very different. And as such, the median is going to be somewhat misleading. So you see that line A, that first set of scores, right? The lower bound is 3 and the higher bound is 22. And the middle scores are 15 and 17, right? So the median would be 16. The bottom set of scores, right, goes from 12 to 22, so that range is quite a bit different. But the fact that the scores in the middle are the same makes the median the same. So even though row A and row B are very, very different, the median is the same. So it's all a question about, is the median really accurately capturing the characteristics of these two sets of data that are in fact quite different? Additionally, it's hard to plug into other formulas, so you're going to see the mean in most other equations, the median not so much. Now on to the mean itself, right? Again, this is the most commonly used central tendency statistic. Again, average and mean tend to be used interchangeably just because so often the mean is the ideal approach for summarizing the central tendency of your data. So the mean, on the other hand, is more so located at what we call the mathematical center of a distribution. So this is going to be a statistic that takes into account the actual numerical weight of all of the values in your data set, and the outcome is going to be derived based on all of the scores in your data set. So really, no information is lost. The way that you get the mean is quite easy. I'm sure you all know how to do it. You add up all the scores in the distribution and divide by the number of scores, so n, right? Sum of x over n. Additionally, you see the mean notated with that x bar, as I've covered. So if you ever see x bar in an equation, that indicates that you are to take the mean of variable x. So you could also see y bar if there's a y variable that you're currently looking at as well. If you ever see a variable notation with a bar over it, you are to take the mean of the variable currently defined as that variable notation. The notation for a population mean is going to be that mu, and you're not going to see that terribly often because more often than not, we're going to be dealing with sample data and not population data. So the mean is going to be sensitive to the exact values of every score in the distribution because, again, it's mathematically derived by summing up every single score and then dividing by the number of scores. So whereas these two data sets that I just showed you have the exact same median despite being very, very different, the mean accurately captures just how different those data sets are. The mode and the median, on the other hand, would be the same, and as such, the mean for these two sets of data is doing the best job at accurately capturing what's going on with these two sets of scores. Even just changing a single score by a single point can affect the mean. As you can see, these two almost identical data sets are only different in that that highest value is 1 point off. The mean takes that into account. So the mean will be impacted by any numerical fluctuation in your data. So you can think about the mean as a mathematical or numerical balance point in your distribution. I'm going to explain what this means theoretically, and it's going to sort of be a bit abstract, but it's going to be extremely relevant when I talk about standard deviation shortly, so try and follow along. When I say the mean is the numerical balance point in the distribution, in mathematical terms, this is that the sum of the deviations around the mean are going to be 0. So what's a deviation? A deviation is the distance of any individual score in your dataset from the mean. The greater the absolute value of a deviation, the further a score is from the mean. Additionally, deviations can be positive or negative because some scores in your dataset are going to be above the mean. As such, they'll have a positive deviation score. There will be some scores in your dataset that are below the mean and as such have a negative deviation score. If you were to sum up the deviation of every single data point in your distribution of scores, it will equal to 0. This is what we mean by mathematical weight. There's a certain numerical weight of all of the positive scores above the mean, and that is necessarily symmetrical with the numerical weight of the scores below the mean. This is inherently and theoretically true about the mean, and this is what we mean by there being numerical balance around the mean. the sum of the weight of the scores above the mean is symmetrical to the sum of the weight below, and as such, the sum of the deviations will always equal 0. Again, this might seem a little bit abstract, but this is definitely going to be relevant later, so I'm going to show you mathematically what this looks like. So let's say you have your set of scores, currently defined as x. Like I said, the deviation is the distance of any score from the mean. So in order to get that, you just take the score minus the mean. As you can see, you get scores, some of which are below the mean, some of which are above. Again, that is because there necessarily will be some scores below the mean and some scores above, unless your mean is 0. That could happen. If not, then the deviations will have some scores below the mean and some above. So if you were to add up all of the scores in that deviation column, it will, if you did the math correctly, sum up to 0. Again, you might be thinking, I am getting way too deep on the mean. It's pretty basic. We all know how to do that. Again, I'm harping on this point because if you understand what's going on here, you're going to have a much easier time at calculating standard deviation in the next installment, which does trip people up just a little bit. So keep this in mind and understanding that the sum of the deviations of the scores inherently add up to 0. All right, so then lastly, some advantages, some pros and cons of the mean. Again, it reflects all of the scores in the distribution, so usually it's the best approach. Usually the mean does the best job at describing what's going on with your data, better than the median or the mode. Additionally, it's very easy to plug into other algebraic equations, which is why you see x bar and y bar in so many equations. So it's very mathematically useful. The problems with the mean are basically going to all be the flip side of the advantages. So all the scores in the distribution do contribute to it. So what that means is that if you have some scores in your data set that highly skew the distribution in a way that sort of confuses or conflates what's going on with your data, the mean is going to be pulled quite strongly by those extreme outliers. So if you have highly skewed distributions or distributions with a few very, very extreme scores, the mean might just not be for you. And again, income is a classic example where the mean is not ideal to use because the fact that there's some mega trillionaires out there greatly changes what the average income is if you were to calculate it. So, for example, if you were to depict income data in the United States, and look at the difference in median to mean income, you'll see that mean income appears kind of startlingly high. Does the average person really make $70,000 a year? No, not really. We think of the median income as a bit more reflective of who's in the middle. $50,000 a year is really much more in step with what we would consider sort of the middle of the road in terms of income. So that's why we tend to use median for income as opposed to mean. Okay, and again, just to demonstrate that the median is very classically used with income, again, you can see that the median income tends to be more reliably used to talk about income because, again, income is a variable that classically shows the sort of limitations of the mean, that there are some circumstances where the fact that it takes into account all the scores in the distribution might actually render it slightly misleading. Okay, additionally, lastly, as you can see with these two separate data sets, the mean being pulled by a single score can be a benefit or a detriment. As you can see with the data set A and the data set B, you have two sets of scores that are identical except for that one rogue score at the end. Again, the idea is that outlier score of 25 in the row B actually indicative of a genuine score, or is it a fluky outlier for whatever reason? You have to be aware of whether or not those scores truly belong in the data set because the mean will definitely be skewed by the presence of a single extreme score. Now, sometimes this whole issue of choosing mean, median versus mode, sometimes it's a bit of a moot point because they might all basically be the same. It kind of depends on the distribution of scores that you're working with. you might have a data set where they all sort of look pretty similar, and so you have a pretty good solid idea of what's a central tendency score. You could really use any of them and not go wrong. If you have data that's quite skewed, though, you might have the mean, median, and mode all being vastly different, and so you really do need to be thoughtful about which score is most effective. Or maybe you just choose to use all of them because you don't want to lose all that information. So as you can see, this graphic depicts a very skewed data distribution depicting coffee consumption. It indicates that most people don't drink coffee, and that you do see the center of the scores based on the median as at around 1.5 cups of coffee. But given that there's some psychos that drink like 20 cups of coffee a week, you do see that that mean is a little bit skewed. So if you have data that looks like this, you do want to be very thoughtful about which central tendency statistic you opt for, because it might make a difference. All right, I'm going to pause there and then pick back up with our variability measures.